Hello and welcome. In this video, we're going to be taking a look at parametric curves. Now, one of those two words is probably already pretty familiar. We know what a curve is already. And a curve might be something where we just have a function. And we've seen other kinds of curves before where we may have to define that curve implicitly as a relationship between x and y. But a parametric curve is a little different. Parametric means that we have a parameter in there. And this flexibility allows us to come up with some pretty interesting graphs that may not be functions and may be pretty complex to even express implicitly. So remember, not all curves can be expressed as functions. Y equals f of x has an implication there that for any value of x, we get a unique value of y. We can use the vertical line test here, and you see I have a ruler, and for a particular value of x, I am crossing through the function in 3 locations. So that would mean that for one value of x, I've got 3 different values of y. That means that this curve is not a function. And as I mentioned earlier, we've seen this kind of behavior before, even just with implicit functions such as a circle. Implicit functions will have an equation that relates x's and y's. And we may choose to think that y is dependent on x, but in order to get a value for y, we need to plug in an x and solve for y, which may or may not be possible. Now, what we're going to be taking a look at with parametric curves is a little different strategy. Let's imagine that this blue curve is the path followed by some kind of particle. If we were to think about this as a path taken by that particle, then we could think about every point on the curve being the position of that particle at some time. And time we might want to represent with a lowercase t. This will allow us to come up with functions for x and y separately as functions of t. So that way we end up with coordinates x comma y as being some function f of t comma some function g of t. And if we don't want to use f and g, we can use another notation where we just simply think of x and y as just being functions of time, x of t and y of t. This gives us what we call a parametric curve, and t here, that idea of possibly time, is our parameter. Whatever we want to choose for t is what we will plug in to these 2 functions to come up with x and y. Now, unlike the domain of a function where we would say the values of x are over some interval, in this case it's the parameter that has an interval. So we call this the parameter domain. The parameter domain is the set of values for which the parameterization is defined. Parameterization is where we take this curve and we define it as some parametric form. Let's take a look at a couple examples of maybe just using table of values to understand how we take a parameter t and give ourselves points on the curve. Now, let's start off with a fairly basic example. Here you can see that x is equal to 2 times t, y is equal to 5 minus 3 times t, and t can be any real number. If we want to start off with a simple strategy for coming up with this shape of this graph, we can do a table of values. The difference here is that a table of values is going to involve input of t and outputs of x and y. Now, because this curve is defined for all real numbers, it might help to maybe choose a few negative values and a few positive values for t. Now, just like with time, we assume that t is going to be in an increasing direction. So as we go from t equal -2 to t equal -1 and so on, these points should be in a particular order, moving from lower t to higher t. So let's start with plugging in t equals -2 into these 2 functions. That gives us an x of -4, and it'll give us a y of 11. So that's our first coordinate in Cartesian coordinates, -4, 11. And we can complete this for the remaining values of t in the table of values. As you see, as t is increasing, it looks like x is increasing and our y is decreasing. You can kind of see that by the linear relationship of x and t as well as with y and t. Now it's time to go ahead and try plotting this curve. And I've tried to make some axes here that will allow us to plot those values. Starting with the lowest value of t in our table of values, -2. That gives us the point -4, 11. So we'll put that as a point here, and we can label that in Cartesian coordinates, but we can also label that as the value of the parameter at that point. Moving to t equals -1, we get -2 comma 8. And when t equals 0, we have x equals 0, y equals 5. And that would give us our y-intercept. Now you can start to see a little bit of shape already here. This looks like a straight line so far, which may not be surprising since the relationship between x and t and the relationship between y and t are both linear. Filling in the remaining points, sure enough, we can see this does form a line. So no surprise there, when we have linear relationships with x and t and y and t, we'll end up with the graph of a straight line. Now, of course, you can see that this does in fact pass the vertical line test, and so we could write this as a function. It'd be pretty simple to do. You would either have to take a look at the slope and the y-intercept of your graph and use a standard form of a line like mx plus b, or if you want, you can actually solve for t in one equation and substitute it into the other and solve for y, and that'll give you the equation of the form y equals a function of x. Let's take a look at another example that might not just be quite so simple and maybe not be a function. In this example, we have nonlinear relationships. X is equal to 2 cosine t and y is equal to 2 sine t. This time the parameter domain is only going to go from 0 to 2 pi. Now, rather than using a table of values in this case, let's see if we can come up with a nice little way to convert this into an equation that we're familiar with. Now, this may not be super obvious, but let's take a look at what we have if we take the x function squared plus the y function squared. That gives us 2 cosine t all squared plus 2 sine t all squared. And if we were to expand those squares and simplify, you can see that we have a common factor of 4 and our identity of sine squared t plus cosine squared t, which is equal to 1. So in the end, this actually gives us the equation of x squared plus y squared equal to 4. We've eliminated the parameter. By eliminating the parameter, now we have an implicit function, and you should hopefully recognize this function as a circle. This x squared plus y squared equals r squared is the standard form of a circle centered at the origin, and in this case, we have a circle of radius 2 centered at the origin 0, 0. So rather than creating points, we can simply just draw that circle. There we go. That's the graph of our circle. However, what might be more important than just knowing the shape here is also knowing where our initial point is and our terminal point. When t equals 0, we can plug that into our values for x and y, and that gives us the point 2, 0. We'll put that point here on the far right-hand side of our circle. When t equals 0, we have the point 2, 0. Now, we have two options as to which way we're going to travel around this circle. And let's see if we can find out what happens by just choosing another value of t. We could use t equal to pi over 4, pi over 3, pi over 6, pi over 2, any of those common values that make trigonometric functions easy to evaluate. But let's just try pi over 2. By plugging in t equal pi over 2, we get x equal to 0 and y equal to 2. And so we can see that the direction of travel around this circle would be counterclockwise. When we get to t equal to 2 pi, though, we'll end up back at the same point that we started. So t equal to 0 and t equal to 2 pi both give us the same point, 2, 0. Now, it's important to know that not all parameterizations are unique. There's more than one way to parameterize this circle. For instance, I could have chosen a different interval for t. Maybe instead of starting at t equals 0, I just want to start at t equal to negative pi and travel as far as t equal pi. Or I could have chosen t to be all real numbers and gone around the circle infinitely many times. But there are several other ways in which I can create quite different equations that involve the same shape. For instance, if I wanted to sort of change the speed at which I'm traveling around the circle, then maybe I'll replace t with 2t, in which case my parameter domain would only need to go from 0 to pi. This is essentially going around the circle faster. I'm going to reach one complete rotation of the circle from 0 to pi instead of having to take from 0 to 2 pi, but it'd be exactly the same shape. What if I were to change the functions, though? If I were to have x equal to 2 sine t and y equal to 2 cosine t, you can still see that it satisfies the relationship x squared plus y squared equals to 4. And you can imagine that because of my parameter domain, I'm going to go around the circle exactly once. The difference here is that when t is equal to 0, x is going to equal 0, and y is going to equal 2. So that means my initial point is going to start at the top of the circle. And from the top of the circle, I can then figure out which direction I'm going to travel by maybe choosing t equal to pi over 2, in which case x is now going to equal to 2 and y is going to equal to 0. So it appears that I'm going to be going around the circle clockwise this time. When t is equal to pi, I will have x equal to 0 and y equal to negative 2, and we can try going around the rest of the circle in the same direction that way. In the end, ultimately, it's a circle of radius 2 centered at the origin, but I'm starting at a different initial point, ending at a different terminal point, and I'm going in a different direction around the circle. So the parameterizations are different, but the shape of them may not be unique. So it can be very easy to actually disguise a very common shape by choosing an unusual parameterization. Take a look at this example. Here I have x equal to cosine squared t, which is cosine t all squared, and y equal to cosine t. My parameter domain is from negative pi to pi. Now, your first intuition here might be because I'm using trigonometric functions, I may end up with something with a circular pattern perhaps. However, if you take a look at the relationship between x and y, the function for x is actually just the function for y squared. By doing a substitution where cosine t is equal to y, we have the relationship x equals y squared, which is a sideways parabola. Now, a parabola, of course, sideways, is not a function, but it's a pretty easy shape to graph. However, our parameter domain is only going to go from negative pi to pi. And you should remember that trigonometric functions, sine t and cosine t, only have a range from negative 1 to 1. So this isn't going to be a full parabola. This is only going to be a partial parabola since x and y can never get larger than 1, and they can never be less than negative 1. If we want to do a quick table of values, we can see that when t is equal to negative pi, x is 1 and y is negative 1. When t is equal to negative pi over 2, x is equal to 0 and y is equal to 0. When t is equal to 0, we have the coordinates 1, 1. And when we reach t equal pi over 2, we've gone back to the same coordinate 0, 0. And when t equals pi, we've gone back to the initial coordinate 1, negative 1. So really, we only have 3 unique points from these 5 different values of t. Let's see if we can plot this curve now. This would imply that we're starting from 1, negative 1 when t is equal to negative pi. And we're going to be following the shape of a parabola to reach 0, 0 when t is equal to negative pi over 2. As we go from t equal negative pi over 2 to t equals 0, then we follow the shape of the parabola and we reach the coordinate 1, 1. Unfortunately, we have to backtrack now because we are going to be increasing in t, but going back to the coordinate 0, 0 when t is equal to pi over 2. So we travel right back along the same path again in the opposite direction. And from t equal pi over 2 to t equal pi, we're going to be backtracking again and reaching the initial coordinate 1, negative 1 when t is equal to pi. So you can see that we've actually traced out the parabola twice, and we only have a partial parabola. Well, as you can see, with parameterizations, we can do some pretty interesting behaviors. It's sometimes very similar to other functions or implicit curves that we've seen in the past. But because of this parameter, we can really manipulate the shape, and we also have an implied direction in which we are traveling along that curve. Now, the first thing we want to do when we come up with a brand new graph system like this, a brand new way of plotting something, is we probably want to take a look at doing calculus on these curves. For instance, what does a derivative mean? What is a tangent line? Let's take a look at that. Let's start off with a parametric curve. So x and y are both functions of t. We could write that as f of t, comma, g of t. What would be the slope of the tangent line to a curve like that at any given point? Well, for convenience, I kind of prefer using the notation x of t and y of t. Your mileage may vary a little bit, It's up to you if you prefer using f and g instead. Well, we know that if we're looking for the slope of a function where y is dependent on x, our slope is dy by dx. It's like rise over run. Unfortunately, here we have y and x being functions of t. That's okay, we can use the chain rule. The derivative of y with respect to t would be equal to the derivative of y with respect to x multiplied by the derivative of x with respect to t. By rearranging that, we can get the derivative dy by dx, which is just equal to dy by dt over dx by dt. And if we're using our notation x of t and y of t, then we can even write this in our function notation. Dy by dx is equal to y prime of t over x prime of t. And this slope is undefined whenever the derivative of x with respect to t is equal to 0. Now, what does it mean for that slope to be undefined? Well, that might mean that the tangent line is vertical, but not necessarily. We can understand that the tangent line is horizontal if the slope is equal to 0. That happens when the derivative of y with respect to t is equal to 0, and the derivative of x with respect to t is non-zero. Therefore, the slope is equal to 0 and not undefined. Now, if the slope is undefined, that doesn't necessarily mean it's vertical. The tangent line is vertical when our x prime of t is equal to 0. It's kind of like saying our horizontal velocity is 0. But we also need y prime of t to not equal 0. That means that we are traveling up or down. If both of these were equal to 0, then we don't really have a slope at that point. If our particle stops moving in all directions, then we don't have an idea of a tangent line. All right, well, we've got the idea of a first derivative. What about a second derivative? For a second derivative, it's not quite as easy as just y double prime of t over x double prime of t. For our first derivative, dy by dx, we found that to get that derivative, we need to take the derivative of y with respect to t and divide that by the derivative of x with respect to t. Now, for the second derivative, in Leibniz notation, that's d squared y by dx squared, what we're doing is we're taking the derivative of the derivative. If we were to follow the same method, then we would have to take the derivative of the derivative with respect to t, and then again divide by dx by dt. So we'll take the derivative dy by dx that we just found, differentiate it with respect to t, our parameter, and then divide by dx by dt. Now, of course, both of these can be written out explicitly in terms of x primes and y primes. We saw that our first derivative could be written as y prime of t over x prime of t, and if we want to plug that into the second formula, we could explicitly come up with a formula for the second derivative. We'd have to take the derivative of y prime over x prime and then divide all of that by x prime. Using the quotient rule and simplifying, we can get that expression. But as you see, this isn't exactly intuitive, and it's not necessarily worthwhile to try to memorize that. Instead, my recommendation would be to memorize that dy by dx is dy by dt over dx by dt, which is pretty straightforward to memorize. And the second derivative would just be involving differentiating that with respect to time, since it would be an expression involving t, and then once again dividing by the derivative of x with respect to t. Now that we've got the idea of a first and second derivative, let's take a look at another example of a parametric curve that is nonlinear and see what we can analyze about that in terms of slopes and concavity. Let's suppose that we have our parametric functions x equal 2t squared minus 8 and y equal t cubed minus 12t. So you can see that both of these are nonlinear. And for a parameter domain, let's assume all real numbers. Well, the first thing that we like to sometimes do to understand maybe the graph of this function is to figure out where the function has horizontal tangent lines or vertical tangent lines. And the idea of finding horizontal tangent lines can be very useful for finding minimum and maximum values of a function. Now, to find the slope of a function, we need the derivative dy by dx. And in this case, that means we need the derivatives of x and y with respect to t. So we might want to treat these as functions. X of t equals 2t squared minus 8, and its derivative is 4t. y of t equals t cubed minus 12t, and its derivative is 3t squared minus 12. And remember that we end up with a horizontal or vertical tangent line when one function's derivative equals 0 and the other does not. Let's start taking a look at the derivatives. Let's start off with x prime of t equal to 0. That gives us t equal to 0. What about when y prime of t equals 0? What about when y prime of t equal to 0? In this case, we'll have to factor. That gives us 3 times t plus 2 times t minus 2, which gives values of t for negative 2 and positive 2. Now, remember, a horizontal tangent line is essentially where our horizontal velocity is non-zero and our vertical velocity is equal to 0. In other words, it is when y prime of t equal to 0 and x prime of t does not. And we can see from our calculations here that that occurs when t is equal to plus or minus 2. Don't forget to check that x prime of plus or minus 2 is non-zero. Now, if we want to find out what points these are on our graph, we can plug those into the original parameterization. T equal to negative 2 gives us the coordinates 0, 16, and t equals positive 2 gives us the coordinate 0, negative 16. A vertical tangent line is going to occur when we essentially have no horizontal velocity, but we do have some vertical velocity. Or in other words, it is going to happen when x prime of t equals 0 and y prime of t is non-zero. You can see that that happens when t equals 0. Luckily, y prime of 0 is equal to minus 12. So this is definitely a vertical tangent line. And by plugging t equals 0 back into our parameterization, this gives us the coordinate negative 8, 0. Now we know how to find horizontal and vertical tangent lines. What if we were just to find the slope at any given point on the curve? Well, I'm going to choose a point here that has kind of a unique behavior, something that's maybe a little bit more unique to parametric curves. Let's take the point 16, 0. And I want to show you that there are actually two different tangent lines at that same point. Now, first of all, since we only have a point 16, 0, what is the actual parameter value? What value of t is going to allow us to pass through that point? If I've told you it's on the curve, then theoretically, there's going to be some value of t that gives us that point. That already actually gives two equations to solve. Tells us that x of t has to equal 16 and y of t has to equal 0. All right, solving these two equations, hopefully they should both agree on the same value of t. The only way we're going to get through this point is if they both agree that they have that coordinate at the same time or parameter t. So in the first equation, we can divide both sides by 2, and we'll have t squared equal to 12. The square root of 12 can be simplified to 2 root 3, and we have to consider both positive and negative values of t. With the equation on the right-hand side, we can factor a t out, and we'll have t squared minus 12. Either t equals 0, or t squared minus 12 equals 0, which gives us those two values of t again, plus or minus 2 root 3. Now, you'll also see that y does equal 0 when t equals 0. But when t equals 0, x is not equal to 16. So we're going to take that point out of there. That's definitely not one of the two parameter values that give us that point. All right, this time around, we're going to actually need to calculate an expression for the derivative. dy by dx is equal to y prime of t over x prime of t, which is 3t squared minus 12 all over 4t. And we can evaluate that at t equals plus or minus 2 root 3. What might be a little bit of a handy notation here is we can write dy by dx with a vertical bar evaluated at t equals negative 2 root 3, which is the same thing as the square root of 12. So in the top, that's going to give us 3 times 12 minus 12, which is 24, all over negative 8 root 3. And we can cancel an 8 in the numerator and denominator, and we can even also rationalize that. 3 over root 3, when we rationalize the denominator, is equal to negative root 3. And so that's the slope of the tangent line at that point 16, 0. But let's not forget that we also have to plug in t equals 2 root 3. That gives us the same value, except in the denominator we have positive 8 root 3, and that simplifies to positive root 3. So you see that we pass through that point twice, one when t equals negative 2 root 3, and once again when t equals positive 2 root 3, and we're going in different directions because the slopes of the two tangent lines at that point are different. Now I'll show you what this looks like in Maple here in a moment, so maybe we can get a better understanding of what this graph might actually look like. But before doing that, there's one more thing that we can take a look at to get a better sense of shape of this curve without having to use a computer. We might be able to also then take a look at the intervals of concavity. Concavity is going to be involving the second derivative now. Remember that the equation for the second derivative is taking the equation of the first derivative and then differentiating that with respect to time and dividing by the derivative dx by dt. So we're going to be needing to take that first derivative, 3t squared minus 12 over 4t, differentiate that with respect to time, and then divide by 4t. Of course, we're going to need to use a quotient rule here, or if you choose, you can simplify 3t squared minus 12 over 4t into two separate fractions. In either case, by simplifying, we should get the second derivative. And our second derivative simplifies to 3t squared plus 12 all over 16t cubed. If you choose, you could factor a 3 out of that numerator. But you'll notice that the numerator is always positive. The denominator is positive whenever t is greater than 0, and the denominator is negative whenever t is less than 0. The second derivative is undefined when t equals 0. In interval notation, that means that this curve is concave up over the interval from 0 to infinity and concave down over the interval from negative infinity to 0. Not including 0 because unfortunately there it's not concave up or concave down. Now at this point in time, I would recommend maybe if you want to just pause the video and see if you can come up with an idea of what this would look like. You could always also include a little table of values in there, plug in some different values of t other than the ones we found, and get a better sense of this shape. But we know where it's got a vertical tangent line, and a couple horizontal tangent lines, and we also have this one point where it seems to crisscross at different slopes. So let's take a look and see what it looks like on a computer now. All right, here in Maple you can see I'm just using the basic old plot command, and for a parametric function we actually have a list of 3 components. The first component is our function x of t, the second component is our function y of t, and the third component is our parameter domain. And here I'm just going to be plotting from t equal negative 4 to positive 4 since most of the points of interest fall within that range. And then I'm just going to plot this graph from x equals negative 10 to 30 and y equals negative 20 to 20. And you can see we end up with this sort of a fish looking shape here. And you can see that we have a horizontal tangent line in 2 locations and a vertical tangent line in 1 location. Those would correspond to our different values of t that we found. When t is equal to negative 2, we have 0, 16. When t is equal to positive 2, we have 0, negative 16. And a vertical tangent line when t equals 0 is at negative 8, 0. And here's that other unique point, 16, 0, and you can see that we would in fact have, yes, 2 different tangent lines. Crosses through that point at very different slopes. And we also have our intervals of concavity. It is concave up for t being from 0 to infinity, which is the bottom half of this fish, and then going off to infinity, and it is concave down from negative infinity to 0, which is the top half of this fish, and also including all of the points way down here that we start at for lower values of t. So our travel around the fish is going to be from bottom right, going around this sort of fish body counterclockwise, and then going off to infinity up to the right. Now, I have one other little demonstration here that hopefully may illustrate how we can interpret these parametric curves as being 2 functions, a function for x and a function for y. This other demonstration here is going to be in Desmos. Now, the way I sometimes like to think about parametric curves is maybe one of a couple different ways. You can think about it, if you've ever played around with an old school Etch-a-Sketch where you have 2 different knobs, one knob goes up and down, one knob goes left and right, and you try to draw a picture with that, then you've already got the idea of a parametric curve. One knob is your x of t, and one knob is your y of t. Now, if you want a maybe slightly more modern example of that, if you've ever played one of those games where you have a whole box of toys and the claw that kind of comes down and tries to grapple a hold of one, well, you have to go left and right, up and down. And again, those are different functions of t, and moving the claw around is very similar. So let's take a look here at this example in Desmos and see if you can kind of make sense of it. When you see a whole lot of stuff in here, don't worry too much. This is going to be our function at the top here in purple, cosine 3t sine 2t. And right now, t is equal to 0. This little slider here will allow me to choose different values of t. For our current value of t equals 0, you can see that I have an x of 1 and sine of 0. So you can see that this blue dot is at x equal to 1, and this red dot is at y equal to 0. Now this blue dot here can only move left and right. It's going to always stay as some value of x at a given point in time, and this red dot is only going to move up and down. And the two parts together will start to draw a curve. So let's start sliding the bar here. Go from t equals 0 and increase a little bit, and you're going to see that my x is going to the left and my y is going up. And these two parts are both giving this purple point. This purple point is a point on my parametric curve for every value of x and y. And as I increase t here, you can see what happens. When I get to, let's say, t equals about 1/2 of pi, 1.57-ish, somewhere around there. Okay, take a look. At t equals roughly pi over 2 here, by plugging that into cosine 3t and sine 2t, I get the coordinate 0, 0. What you can see what's actually happened is that my blue curve here, which is my x of t, has started from 1, gone to -1, and come back. Whereas my y of t function has gone from 0 to 1 and back to 0. And then we're continuing to increase t and see what happens with x, which is the blue dot, and y, which is the red dot, and the two components together give us the location of a point on our parametric curve. Now let's just play this out and let t go all the way up to 2 pi, and you should see that even though our x and y are just going from -1 to 1, because of the unique periods of those two different functions, we end up with a pretty interesting looking graph here. And when we get to t equals 2 pi, we end up back at our initial location. So think about x of t as just adjusting our Etch-a-Sketch left and right. Y of t is adjusting up and down. The two pieces put together end up giving us our parametric curve. And there we go. Hopefully that gives you a pretty good understanding about how we can take a curve in terms of parameter and sketch it, as well as do a little bit of calculus on it. This is going to help us out greatly because in multiple dimensions, it may be really just a requirement to be able to express something in terms of a parameter. And what we'll see in another video coming up here is that oftentimes if we want to express a curve in something other than x and y, it can be a lot easier. And that would be a good example of where we come up with polar coordinates. So stay tuned. Thanks for watching, and I'll see you in the next video.